Hello everyone, this is the compiler that I've written for CSCI E-95. So first, some information about my development process. This is my largest project by far. It's around 10,000 lines of C code, not including the Flex and Bison generated files. For my prior experience, I've been programming for maybe 3 to 4 years. Most of that has been in other languages, but I've written around 2,000 lines of very C-like C++. And for C, I'd only seen it in books, where I'd glossed over malloc calls and not learned much about C. So over the course of this project, I definitely learned a lot about C. And I also got to learn a lot about GDB and Valgrind, which were two tools that I used while I was developing my project. One thing that was really interesting was in the final problem sets, especially the MIPS generation, you get a decent idea about how these tools actually work, which was really cool. For my testing, it was fairly unstructured. I didn't use any sort of unit testing framework. I would just start with a fairly empty C file and incrementally add things as I added features to whatever problem set I was working on. Okay, so what language are we compiling? We are compiling C89 with the following restrictions and some other ones which are less noteworthy. So we have no preprocessor macros, no switch case statements. Only a single file is allowed as input. We don't link, so you can't link your standard library, although we do have access to syscalls, which let you do quite a bit. There's no structs and no enums. Okay, so first an overview of the stages of the compiler. First, we have Elixir, which converts our sort of unstructured input to a stream of tokens, and you'll see what those look like later. Next, we have the parser, which breaks down this token stream into a tree and makes it a lot more manageable to work with. Third, we have symbol table management, which essentially looks at variables and functions and stores information about where they're defined and where they're referenced, and applies that information to improve the usefulness of our abstract syntax tree. Fourth, we have type checking, which assigns a type to every sub-expression. So, for example, if we have I plus 6 in our code, I would get assigned a type, 6 would get assigned a type, I plus 6, which is its own node, would also get assigned a type. In this stage, we also make sure that all of our operations have correct input types, correct output types. We aren't trying to modify immutable things. So that all goes on in the fourth stage. In the fifth stage, we have intermediate representation. So we go through our tree, which has no errors in it, thanks to the previous 4 stages, and we generate something which looks very much like assembly, but has a few key assumptions which make things much easier. And then finally, we have the code generation, where we take our intermediate representation and do a pretty one-to-one translation to MIPS 32. Okay, so first lexing. This creates a stream of tokens from our input, and for this I use Flex, which is an open source lexical analysis generator based on Lex. And you specify tokens in a Lex file using regular expressions. So if you look here on the bottom, this is just a screenshot from my .lex file. And on the left, you'll see I have regular expressions, which define tokens. And on the right, I have code, which is associated with each regular expression. So first, I just have some basic ones, which just return identifiers for the token. And then on the bottom, I have a slightly more complex one for identifiers. And on the right, you can see what a program might look like after this stage. So we have the token type, we have lines, we have start and end columns, and we have other information which wouldn't fit on the slide for each token. Okay, second, we have parsing, which creates an AST from a token stream, the output of the last slide. And the idea of parsing is that every expression or definition can be broken down into smaller components until all you have are tiny things like the number 3 or an identifier. And you can think of this step as parenthesizing every expression into sub-expressions. And so here on the left, you can see a small test program we'll be working with. And on the right, you can see it after it's been parsed and parenthesized into sub-expressions. Okay, symbol tables. So in this step, we keep track of variables, where they're defined, where they're used, what are the types of the variables. We also track labels, such as used in go-to statements, functions, and string literals. So on the left, we have the same code, and on the right, we have the symbol table. And you can see that we have a root symbol table, which contains all of our functions, and then each of those functions has an associated symbol table lower down in the output, which contains variables for the parameters as well as automatic or local variables in the function. At the very bottom, we also have this empty symbol table for the for loop. Also, in this stage, we replace identifiers in the AST with references to their symbol table entry. This makes it much easier to access relevant information down the line in later stages. So fourth, we have type checking. In this step, we have to annotate each AST node with its type if applicable, right? So in this case, declarations obviously don't have a type, but something like A plus C would, right? So you basically go down through your syntax tree and assign every node that you can a type. And you also have to make sure when you assign that type that the types of the children match and are allowed for the current node. So on the far left here, we can see we have an invalid program because we're trying to assign C to 6, which doesn't work. And so in the type checking stage, we'll get an error that we're trying to assign to an R value. Now in the middle, we have a valid program. And then on the right, you can see that we're also inserting casts, which are implicit in the code, but we make them explicit here in this stage. All right, so next we have intermediate representation. This is almost assembly. Most IR instructions generate maybe 1 or 2 MIPS instructions, but also there are a few key differences in the actual code. So for IR, we assume an infinite number of registers. This is to help make optimizations a little bit easier to perform, but obviously in MIPS, we only have 32/18 registers to work with, and so this is impossible. The other difference is that we're still referring to variables by their names, and variables don't have names in MIPS. You just have stack offsets, so this is not allowed. All right, finally, we have MIPS code generation, and this is the end of the line. We have to do a couple things. We first calculate stack offsets for all our local variables. So eliminating their names, variables no longer have names at this stage. We also check whether spill registers are required. So when we're computing an expression, do we need to maybe spill some of the registers onto the stack? We also, using this information, have to go through the IR and step-by-step translate it into MIPS assembly. Okay, so now let's actually run some code. All right, so next we're just gonna run this small example, which calculates Fibonacci numbers. And I have a custom make target, which makes things a lot easier. And we can see that we've printed the first 30 Fibonacci numbers. Yay.